Okay, so this is a supplemental section. It's actually going to supplement the things that we're going to be doing in 15.8 and 15.9. Technically, this section is typically taught, believe it or not, way back at the end of chapter 12. I'm not really sure why it was stuck there in the first place, since you don't really need it till now, but here it is. We are talking about two new ways of defining coordinates. Specifically, we're going to go through what are called cylindrical coordinates and spherical coordinates. We've done this kind of thing in 2 dimensions before. We actually took something which was in your typical Cartesian or rectangular coordinate plane, and we also learned how to do it in polar, which was basically based upon circles and angles. Well, this stuff is actually just an extension in 3 dimensions of that. So we're going to be able to graph points in both cylindrical and spherical coordinate systems and then apply those systems to equations. So let's talk about, first of all, cylindrical. And the good thing is we've actually kind of already done this. We just didn't call it necessarily cylindrical coordinates. Because of what we've done is we've changed things into polar from 3 dimensions for the last couple of variables. It's the same general idea. So here's the general idea of a rectangular coordinate. This is what we've been dealing with. So let's say that we want to just do the point, we'll make it easy, 1, 2, 3. In rectangular coordinates, the first component is x, second component is y, and third component is z. So it means that I would go out 1 unit in the x direction, 2 units in the y direction, and 3 units in the z direction. So 1, 2, 3. And then you would have your point. In cylindrical, it's the same idea really as polar. So let's do a cylindrical coordinate. So in cylindrical, it's really, like I said, it's an extension of polar. Cylindrical coordinates are based upon a radius, an angle, and then the nice thing is z. So if you remember from polar coordinates, the r represents the radius from the pole, which in this case is going to be basically the same place as the xyz origin. So this right here is considered the pole. And so I'm going to have some kind of an angle which is going to be created. Let's just make the angle over here, whatever this is. You're going to have your angle which is created from the positive x-axis. So that'll be your theta. You're going to have some kind of a radius, so it will stop out here. So this would be considered r. And then you're just going to have a z value, which I will do in orange, which basically just extends vertically. And it could be vertically up, vertically down, just depends on what point it is. So you are going to have an angle created with the positive x-axis, a radius, which is the length from the pole out to basically where the projection of the point would be into the xy plane, and then the vertical distance z. That's it. That's cylindrical. So really the only thing that changes here is the fact that we are changing from x and y to polar. Z is just z. Okay, I did not obviously do the point. That's not obviously the point 1, 2, 3 over there. I just wanted to show you the general idea. So let's go ahead and look at a couple of formulas, or formulae, or formulae. I don't know how you say that, to be honest with you. I think it's formulae that we might need. So again, let's kind of sketch once again in 3 dimensions how we're going to look at this. So again, we've got our, whatever this is out here, that's going to be our length to this particular point. This particular point would be an x, y, and 0. And then if we were to extend that to whatever the point is that we're interested in, that point is going to be x, y, z. Okay, so now if we put this into polar, it's going to get us to exactly the same place, but we're going to have to use different methods. So again, this piece right here, the length from the pole out to the projected point down into the XY plane is your radius. The angle which we make from the positive x-axis is theta. And I kind of forgot to put this down here. We'll go ahead and write this in. This was your x value. This was your y value. So that was x, that was y, and then the vertical part was z. Instead, like I said, for polar, it's going to be the r, the theta, and still the z. So here are some of the formulae, however you say this, I'm not even sure if this is a real word, that you're going to need. Based upon Pythagorean theorem, we know that we can find the distance for r because that's going to be the hypotenuse of the right triangle if we are given the x and the y, and we have to be given the x, y, z point in order to change it into a cylindrical. So we know that x squared plus y squared equals r squared. Again, Pythagorean theorem, also the equation for a circle centered at the origin where the radius is r. To find the angle, well, let's see, the angle, we could use r if we really wanted to, but the most common form that we're going to use is the fact that tangent of that angle is opposite over hypotenuse, which is y over x. So that's going to be a way for us to get theta. Now you'll have to think of it in terms of what angle would give me the value. It's not really an inverse, although you're kind of doing that purpose. And then z is just z. So that's a way that we're going to be able to find r, theta, and z. And a couple other things that you'll probably need to know is you'll need to remember that x itself is r cosine theta and y is r sine theta. All right, given those pieces of information, again, most of this should be review. All the stuff on the right side in those formulae really is exactly the same thing as polar with the exception of the z. Everything else is just polar transformations. So let's go ahead and do one. We want to convert the point 2 pi force 1 from cylindrical back to rectangular. Okay, this is actually the easiest way to go, from cylindrical to rectangular. So we're going from r, theta, z back to x, y, z. Well, z is z either way, so that's the easy part. So we just need to find x. Well, x is r cosine of theta. So it's 2 cosine of pi fourths. Cosine of pi fourths is square root of 2 over 2 times the 2 is just going to give us root 2. Y is r 2 sine theta, sine of pi fourths, which just happens to be exactly the same thing since cosine and sine of pi fourths are the same. So we get square root of 2 there, and then again z is just 1. So our rectangular coordinate would be square root of 2, square root of 2, 1. And that's how we would transform something from cylindrical back to rectangular. That by far is the easier way to go. Now let's take one that's actually in rectangular and put it into cylindrical. Again, it's not extremely difficult, but you do have to remember the formulas. I tend to find r first, although it doesn't matter, you can find theta first. Again, z is just z, so that makes that part easy. So let's find r, which is x squared plus y squared equals r squared. And then we've got 1 plus 1, which is 2. So r is going to equal the square root of 2. Technically, it is the plus or minus square root of 2. For our purposes, we are going to deal with the positive radius. Remember that there's no such thing technically as a negative radius. It just means that whatever your angle is, you're going to go in the opposite direction with that radius. So if you had an angle of pi, then you would actually have to go backwards, so it would be on the same place as the angle of 0, even though it's not really an angle of 0, if you used a negative radius. We're going to go with the primary in this case, which is the positive. I will write both angles just so you can see them. We do need to find the angle, so let's find theta, and that's tangent theta equals y over x, or -1. So where does theta, what angle of theta gives you tangent of theta equals -1? So theta is going to be at 3 pi fourths and 7 pi fourths, because those are the quadrants in 2 dimensions where tangent is negative. So the question then becomes, well, which one do I use with which? Well, that kind of comes from knowing the original point. The original point, given the fact that it's 1, -1, 4, is going to be in, again, if you do a 2-dimensional projection of this, that would be in what would normally be considered the 4th quadrant, because you'd go right 1 and then down 1. So that means that the 7 pi over 4 is actually going to be the one that goes with your positive radius of square root of 2. So square root of 2, 7 pi fourths, there's r theta, and then z is just z. And as I mentioned, this is the way you're going to do it for the most part. You might see a question where it asks you, or give me the alternative way of writing this with the negative radius. So if you use the negative radius, well, that means that the angle has to be on the opposite side. So that would be the 3 pi fourths. And then the z value is still just z. But the one that's in the box is the primary way to see it. So that's the way we'll use it for the most part. And really, that's all there is to cylindrical coordinates. We'll deal with changing things into cylindrical equations at the end. But that's cylindrical coordinates, basically polar with z. Now let's talk about spherical coordinates. This one's going to take a little bit longer to develop. It's not extraordinarily long, but we haven't really seen this idea specifically. So the idea is that we can still get to any point in space basically by using concentric spheres. What does that mean? So without trying to draw this exceptionally well, because I'm going to probably erase this, but we'll see. If I were to draw a sphere here, so it looks something like that, and then I could draw a bigger sphere around the origin, so it's going to look something like that. And then I can draw a bigger sphere around the origin, so it'll look something like that. And you can see why I'm going to stop drawing this, because it's going to get very messy. But the idea is I can use concentric spheres from the origin to find any point, any location out on the 3-dimensional plane. So maybe I have a point which is right on the edge of that, oops, it's supposed to be in red, on the edge of that sphere, somewhere right there. Maybe that's the point I'm interested in. It might be easier to locate that point using spherical coordinates. So how do we actually write spherical coordinates? Now this one is going to be a little bit different. So let's go ahead and put a slightly larger 3-dimensional coordinate plane on here. All right, so the idea is we are going to get to a spherical coordinate someplace, and I'm going to try my best to write this. Still going to start with the rectangular idea. So I'm still going to start with the idea that I've got some kind of an x value. I'm going to have some kind of a y value. And then we're going to have some kind of a z value. I'm making that relatively tall, so I have a little bit of room. Okay, that's a rectangular coordinate. If we do this using a sphere, now what you need to think about is there's a sphere that I can draw which is centered at the origin that's going to go through, or the outside of the sphere will hit that point that I put at the top that I'm just kind of even making bigger now. A sphere, there's a certain size of a sphere that I can get there. Well, how do we find the values of that sphere? Well, we know that from the origin, or from the pole, I can still create a radius. And that radius still has an angle which is made from the positive x-axis, and we'll call that theta. Okay, that part of it, the theta part, is actually still going to be part of this. The radius, however, is not what we're looking for. We are actually looking for specifically, let's do this in orange, the distance from the pole up to that point. Okay, that's a different distance than the radius part, because the radius is what it is as the projection down into the 2-dimensional plane. The blue and the orange distances are completely, well, for the most part, they should be different. I suppose you could get one that's the same, but that would be lucky. Here's the thing. This vertical, that Z, that green Z value, makes a perpendicular with the XY plane, which makes the triangle that you see from, as a matter of fact, let me erase that red mark, which makes the triangle down to the blue line, that makes that triangle a right triangle. So what you've got is R is one leg, Z is another leg, and the distance in orange would be like your hypotenuse. We're going to call that rho, not to be confused with the rho that we typically use for mass or density, excuse me. Okay, there's another angle which is created between here. Whoops, that's supposed to be in red, which is right there. We are going to call that angle phi. Now, the nice thing is that the Z value that we have in green and the Z axis itself are parallel. The orange part is what's called a transversal from back in geometry. We have a transversal which is cutting in between two parallel lines, which means that the alternate interior angles are equal. So the angle phi that I have in red is exactly the same angle as this angle, and we're also going to call that phi by alternate interior angles. So spherical coordinates are going to be based upon rho, which is basically the radius of the sphere, theta, which is the angle which is made with the positive x-axis and r, and then phi, which is the angle which is made with the positive z-axis to rho. So phi is the angle which is made from the positive z-axis to rho. We call this the angle of Bloom. And it's called the angle of Bloom because if you think about it, if you have a flower basically starts vertical, and then as it starts to open up, it blooms. Well, basically, if you were to put a z-axis straight down through the center of the flower, what the petals do as they're starting to open up, that creates the angle of Bloom. That's kind of what it's called. I don't know if that's an official name, but it's kind of what everybody's accepted it as. So here are our coordinates. Again, it is rho, and again, that is pronounced R-H-O, rho, or R-O-W. I think it's actually spelled R-H-O in English when it's translated. Theta, which is the angle made with the positive x-axis and r, and then phi, which is the angle made with the positive z-axis and rho. And again, this is what we call, this last one is called the angle of Bloom. How much does this specific thing open up from the positive z-axis? And it opens up all the way around the z-axis in every direction. So here are your spherical coordinates. Written in the correct order, it is rho, theta, phi. That's spherical coordinates. So we're going to need some equations. We're going to need some ways to translate these things. Hopefully these equations will help to get from either rectangular or from cylindrical to spherical. So here's our equations. The first equation. First equation says that r squared plus z squared, let's look at those. R squared plus z squared equals rho squared. That's the Pythagorean theorem of kind of that vertical standing triangle that I was defining earlier. R squared plus z squared equals rho squared. So that's actually a way to get from cylindrical into rho, which is spherical. But you could also look at this as, well, we know what r squared is in 2 dimensions. That is x squared plus y squared, and then don't forget your plus z squared equals rho squared. And if you're really thinking about it, once again, that should make sense. That is your standard form of a sphere centered at the origin with a radius of rho. So more than likely you'll use this one. As long as you know that x squared plus y squared is r squared, then you can also use it from cylindrical as well. All right, number 2. There are 4 of these. Well, technically it's 5. Cosine of phi, because we got to be able to figure out phi. So let's go back up here. Well, phi is the angle in red. So if we look at the interior angle in red, the one that's actually within the triangle, cosine of that angle is the adjacent over the hypotenuse. The adjacent is z, hypotenuse is rho. So cosine of phi equals z over rho. So in order to find rho, you kind of, in order to find phi, you're actually kind of going to need, the rho part first. Or if for whatever reason you needed to solve this for z, then you would just multiply both sides by rho. So z is going to equal rho cosine phi. So again, this is a way to change things into any of the forms. So you can use this equation and then just manipulate it to figure out what do I need phi, what do I need to find z, whichever one. Number 3 is I need to have the equation sine of phi. And why would I need sine of phi? Well, sine of phi, looking at this, is going to be the opposite over the hypotenuse, which is going to be r over rho. So if I wanted to solve that one for r, just multiply both sides by rho, and that'll get you r. So that would be a way to get r out of this. And then the last one, which is really a set of 2 equations. Basically, this is a way to find x and y if we need it. If you think of this in terms of polar, x equals r cosine theta. Well, r is rho sine of phi. R is rho sine phi. So x equals r cosine theta. R is rho sine phi cosine theta. Likewise, y is r sine theta. So r, once again, is rho sine phi sine theta. And that's a way that you can get x and y from spherical coordinates. All of this stuff is just developed from the right triangles above. All right, that is plenty long enough for this video. We will come back and do a few transformations of points, and then we'll get into some examples of equations.